nanoHUB.org.
Online simulation and more for nanotechnology.
Then after we have learned from Maxwell's equation that an electromagnetic wave is a result of the time-varying electric field giving rise to time-varying magnetic field and so on, we can combine the equations number 3, equation number 4, that describe this variation and this interlocked relation between E and H, and combine them together to give us what is called the wave equation. The wave equation is this equation, and we read it as Laplacian square of E, and E, remember, is a function of space and time, equals mu and epsilon, mu epsilon multiplied by each other's, multiplied by the second derivative of the electric field vector with time. And actually, this is valid for a source-free medium where we set rho, the free charge, and J, the current, equals to 0. The free current equals to 0. After doing that, we reach to this wave equation whose solution is well known, and it gives us the harmonic dependence of field with time. So we have E, which is a vector of R, and T is the real part of an amplitude that is just a function of position or space and a time harmonic function. This time harmonic function helps us to drop the time dependence further on when we do the derivative with time. And we help us as well to define the velocity of the wave, which is V equals to 1 over the square root of mu epsilon. Now, what is especially important for us is this part of the solution, which is the position-dependent or the space-dependent solution or amplitude, that is E node of R. And we call that the Phasor representation of the field. The Phasor representation can be solved for after we simplify the equation when we drop the time dependence by dropping the derivative with time to minus omega square. It gives us the homogeneous vector Helmholtz equation, which is time-independent wave equation, from which we can know the solution of the Phasor fields of the electric field in this equation, which is a forward wave and a backward wave, whose amplitudes E node plus or E node minus depend on the generating source and the boundary conditions, which tells us whether we have a forward traveling wave in the positive direction or a backward traveling wave in the negative direction. And in fact, we can take that constant and we call it K, or K squared, like omega over V. All of it is squared. So K is omega over V. Omega is actually, we have defined it as a time harmonic dependent field. So omega describes the time frequency of the wave. Now K will describe the wavelength of the wave in space. So K is 2 pi over lambda, but K equals omega square root of the product of mu and epsilon, from which we can define the refractive index of a medium. And actually, the refractive index is the relation between the speed of light and the phase velocity in that medium. Remember that the phase velocity depends on the constituent parameters in the medium, which is mu and epsilon. So N tells us about the constituent parameters. And because V is always less than the speed of light, the velocity of the wave is always less than the speed of light, this quantity, the refractive index, is always larger than 1. Like for well-known dielectric material. Now, we can also make the same exercise for the H vector, or we can use Maxwell's equation to define a relation between the phasor magnetic representation of the magnetic field, from which we can learn that H is the product, the cross product between the propagation vector K and the electric field phasor E node. And from this relation also we can learn that the relation between the H node and E node equals to what is called the intrinsic impedance independent of the electric field and magnetic field, just depends on the medium where the wave travels, depends on the ratio between mu node and epsilon node here defined in free space. And also from this cross product from matrices, we can learn, or from the vector product, we can learn that we can form a right-hand triplet from E, H, and K. Now, look at this example. For in this example, if you point to the propagation direction with your thumb, your pointer will point to the electric field direction, the electric field vector direction, and the magnetic field will be into your middle finger. So in here, we can describe it in this description. For example, if you put K, like here, K, like in this direction, E will be the electric field will be towards your pointer, so put your thumb towards K. E will be the red vector, and H will be out of the plane of the screen. And make sure that it follows the right-hand rule. Now, if we take that and if we wanted to apply that to our problem, let's think about a very simple problem. That if we have a traveling wave hitting an interface between two different medium. Medium number one, for example, is free space, and medium number two, say, is glass or plastic or PMMA or any material you can imagine. Each medium is described by its refractive index N1 and N2. So we have the traveling wave going through the interface between the two media. And as it hits the interface, some of the power is reflected back, traveling in the negative z direction, and some of the power is transmitted to the medium number two. And we can describe the relation between the magnitude of the reflected field and the magnitude of the transmitted field to the magnitude of the incident field. So now we know that each vector triplet E, H, and the propagation direction form a right-hand rule. For the incident wave, E, I node, and say for the magnetic wave, let's say HI node, we can find a relation between EI node and ER node of the reflected field and the incident field. And this is actually done by solving for boundary conditions at the interface, and the boundary conditions are derived and are well known from Maxwell's equations. But what we wanted to know here is what we call the reflection and the transmission coefficients, because these are the quantities that will be solved for in S4. These will be the quantities you will look for in your simulation. And we define R, or the reflection coefficient, as the relation or the ratio between ER node, the reflected field amplitude, and EI node, the incident field magnitude. So the reflected field magnitude and the incident field magnitude, the absolute value squared. And of course, because of the conservation of power, the amount of transmitted power in a lossless medium will be 1 minus the reflected power, the incident power minus the reflected power. So T, the transmission coefficient, equals 1 minus R. For normal incidence, which means that the incident wave is incident at an angle equal to 0, And you will learn more about the definition of the incident angle in the tutorial, which is the angle between the propagation direction and the a line perpendicular to the surface or the interface. So the angle between the propagation direction and this line equals to 0. It means that the incident angle of 0, it means that we are at normal incidence. So these are well-known relations for the reflection coefficient, transmission coefficients only for normal incidence for lossless media between two different media.